Wonderful. Thanks so much for joining us.
Thank you for having me. I am so excited to be here. This is a wonderful conference about which I knew nothing until this year, but that's going to change. My graduate students are all coming next year for sure. So I'll talk a little bit about machine learning in criminal justice, and I suspect this is not an area you have heard of a whole lot about, so at least this is going to be new for you. Let me start by introducing you to Mr. Stinson, Robert Lee Stinson. Back in 1982, his next door neighbor, a woman that was 61 years old, was stabbed and beaten to death and raped. And there was no evidence. So the only evidence that they could find was 8 bite marks that they found on the cadaver. And so the police a forensic odontologist said, this bite mark must have been made by somebody missing a front tooth. And so the police canvassing the neighborhood happened to interview Mr. Stinson, and what do you know? He was missing a front tooth. And so that was the end of him. They accused him of the murder. Never mind that it was the wrong front tooth, but details. They accused him of the murder. He went to jail, claiming all the time that he was not the person who had actually killed this woman. He spent 23 years in jail. It turns out he was not the culprit. So after 23 years, DNA evidence that was recovered from the saliva on the body was finally analyzed. The Innocence Project was behind this case, and he was set free. This is unfortunately something that has happened a whole lot of times. And so there have been so many blunders and so many scandals associated with the mishandling of forensic evidence that in 2009, the National Research Council published this report that I'm showing you there. And this report was tremendously critical of the forensic sciences in general. So it said that the forensic disciplines had no scientific validity, most of them at least. They were rife with subjectivity. And in particular, pattern evidence was singled out as most lacking in any scientific foundations. So what do I mean by pattern evidence? So what's known as pattern is bite marks, what you know, handwriting, firearms examination, shoe prints, fingerprints, everything in general that leaves an image. And so that's what I'm going to be talking about today. So before we can talk about forensic sciences and what are the problems there, let's think about what a forensic practitioner does. So a forensic practitioner typically provides the information that is needed to answer one of 2 questions, and these are questions of source. So the first question is the suspect the source of the evidence that was found at the crime scene? That's called a specific source question. There's also something called the common source question. So were these 2 bullets found at 2 different crime scenes fired by the same gun, for example? So that's a common source question. And this is easier than this is harder than it looks, I should say. So what I'm showing you down there are 3 different cases. The first one is fingerprint evidence, and you have some smudged latent print found at the crime scene. Then you have this perfect print from the suspect, and the question is, did the suspect leave that smudge print at the crime scene? The one in the middle in green, those are the bottom, those are cartridge cases, and when ammunition is fired, the gun leaves some markings on the base of the cartridge case that firearms examiners use to compare cartridge cases. And the last one is shoe prints. Those are particularly difficult. And you tell me, can you tell in any of these 3 cases whether the suspect may have been the source of the evidence in the crime scene? So there's any number of challenges. Challenge number 1 is that except for DNA, and those of you, except for DNA, most of the disciplines rely on very subjective assessments. I'll repeat this phrase at some point, but it's common to hear from a forensic practitioner, these 2 things are a match, and how do you know these are a match? I know a match when I see one. Yeah, I know. Forensic measurements, one has to be honest. I mean, it's hard to obtain measurements to begin with. And when one does get to measure anything, these measurements do not lend themselves to the standard statistical modeling, like writing a mixed model or a nonlinear model or whatever it is. And so you sort of don't have those tools at your disposal. The data tend to be highly multivariate, very non-normal, so everything you don't want to see in data. And oftentimes you end up with images, so you just have two images that you want to compare. And as you know, images are composed of many, many thousands of pixels, and this can get pretty challenging pretty fast. So machine learning actually might be a good alternative, and there's been a push to start using machine learning in criminal justice for some years now. And you probably have heard about machine learning in like prediction modeling. As a matter of fact, this morning we talked about trying to predict who's going to commit a crime again. This is one area. I'm not going to talk about that. For me, my subjects are evidence. So it's not human subjects, it's evidence. But of course, the evidence links you to human subjects. So the ultimate goal here is to answer the question of source. And so you can think about this in two steps, right? So the first thing you might want to do is you might say, all right, so I have these two samples, one from the crime scene, one from the suspect. Let me see how similar these two things are. So you might want to quantify the degree of similarity between the two samples. But that doesn't tell you the whole story, right? So the next question is, how significant is that degree of similarity? This is what's called the probative value of the evidence. If you would observe a high degree of similarity only when the two samples have the same source, then you have highly probative evidence. If you would observe this degree of similarity anytime, then of course your evidence is not probative at all. So there's two pieces to this story, and machine learning can actually play a role in both of those pieces. So let's start with quantifying the degree of similarity. So what are we going to try and do here is we're going to try and estimate a score, some sort of a score that quantifies the similarity between two items. And the first thing you think about as a data scientist is what type of data you might need. So of course you need a very, very large data set to train your algorithms. And for those items in your training data, of course, you have to know ground truth. So you have to know what the correct labels are for each item. And then, of course, you have to have another very large and realistic data set to test your algorithm and get some sort of good estimates of error rates and so on. So you also need to know if you're going to be using supervised learning algorithms, you need to know what kind of features you're going to be using to compute the score. And it turns out that in some cases, selecting good features is not that trivial. In some cases, it's not bad, but in some cases, it's not that trivial. And let me use the example of a fingerprint. So what would you use as a feature in a fingerprint? So fingerprints have whorls and loops and bifurcations and ridges that end and so on. But it's not only the number of each one of those features, it's the geometric arrangement of them. So you might think about measuring perhaps the distance between the two closest features and the angle between the features, and in general trying to understand what the geometric arrangement of these minutiae, like they call, and then use those as your features in your classifier. I am going to talk from now on about the specific case of firearms examination. Again, a topic I know you probably know a whole lot about. I am showing you there a bullet. Now, bullet is where we think when we talk about firearms. It turns out that bullet is just the projectile that is expelled from the barrel of the firearm when it is fired. And inside the barrel of a gun, there's something called rifling, and rifling is just a set of indentations that impart rotation to the bullet as the bullet leaves the barrel. And it's just meant to improve stability of the bullet in flight. So that's done on purpose. But there's also a bunch of micro defects in the barrel that impart other striations, other marks on bullets. And those are the ones that firearms examiners use in order to say these two bullets match or not. So the schematic there shows you the groove areas and the land areas, and you see a little red rectangle over there. That's the piece, that's where the striations are that the firearms examiners look at. So you would think that if 2 bullets were fired from the same gun, they would have comparable striations, right? So they would be the same. So that's going to be the game here. So here on the left-hand side, or the right-hand side for you, I'm showing you a firearms examiner, and she is doing what firearms examiners do. She has the 2 samples. She's using something called a comparison microscope, which sounds very, very fancy, but it's just 2 ordinary optical microscopes, one next to the other. She puts a sample on the one, and in the other microscope, she fiddles with the controls and rotates the other sample until she finds striations that match, whatever that may mean. And what I'm showing you there on the other figure, the red line separates the 2 images. And the striations, what they look at is to see how many of those cut across. And so they say, oh, there's 7 striations that cut across, match. Or there's no striations that cut across, no match. So the conclusions that they make are purely categorical. Match, do not match, inconclusive. And those decisions are completely subjective. There is no threshold, for example, to say you have to have 17 striations that match in order for you to declare a match. So with the exact same set of samples, 2 firearms examiners may come up with very different conclusions. So what are we doing in my center? So what we're doing is we're trying to put some objectivity in this entire game. What I'm showing you there is an image from a confocal microscope. So we use 3D, we look at the surface topography of the bullets. And so the area that we focus on is that area that's marked in red. So the two white lines there represent the end of the land area. Then come the grooves, then comes another land area, another set of grooves, and so on and so forth. We just look at that area shaded in red there. What I'm showing you now is a cross-section of that. So I'm now flipping this thing over and looking at a cross-section. And you can see where the 2 grooves start on the side. And so the bottom image there is already, we start processing this data, and I'm showing you a single pixel representation of that land, and still with the groove areas and so on. So there's any number of steps that happen now. We automatically detect the grooves, remove those pixels from the image, and after a lot more cleaning, on the top there, you can see that land with a blue curve that's superimposed on it. That's just a Loess curve. And what we are interested in is the residuals of that curve fitting. So at the bottom there, what I'm plotting there are the residuals from that Loess fit. And this is what we call the signature of a bullet. And so those ups and downs, those peaks and valleys correspond to the striations. And now, lo and behold, we have something that we can measure. And so we take, yes, it's fabulous. And so now we take, the next thing we do is we say, all right, here I have 2 bullets. Were they fired from the same gun or not? And so the first thing we do, of course, is we superimpose them and align the signatures so that they fit. And then start measuring things, right? So now I can measure, for example, the difference in the heights and in the heights of the peaks and the depths of the valleys. I can measure the distance between peaks. I can measure any number of things, and we have defined 7 features that work very well for us. And with those 7 features now, we're in the game, right? So now we have those 7 features. We can combine them into some sort of a score and use that score to quantify the degree of similarity between these samples. And so we combine those features. We use a random forest. We tried support vector machines, neural nets, all kinds of other things. And the reason we ended up kind of working with random forest is that they seem to be the easiest ones to explain to forensic practitioners. And so go explain a support vector machine. So the scores between 0 and 1 is what we get. And of course, 1 indicates high degree of similarity, 0 indicates very low degree of similarity. And this is an example. We trained our random forest on this one experimental set of bullets. And you can see that the separation was perfect. So in the dark blue, we have the scores that correspond to pairs of bullets that we know were fired from different guns. In the light blue, we have pairs of bullets that we know were fired from the same gun. This is like heaven. But of course, the proof of the pudding is in the eating, right? So how well does this algorithm work if you apply it to a different data set? And so we sort of extended a challenge, and we started getting sets of bullets from all kinds of police departments and crime labs across the country. And I have to say that until now, we are 0 for 1. We have not made a single mistake. And yeah. Of course, there's more to be done, but here's one of the sets of bullets that we work with. This is from the Phoenix Police Department. And, they send us a set, and they don't tell us which matches with what. In fact, they don't even tell us whether some bullets have a match in that particular data set. So we need to decide all that stuff. And so this is the distribution of those similarity scores that we got among the matches. Afterwards, they tell us, right? So these are the similarity scores that we got among the matches and the non-matches. And as you can see, there's very nice degree of separation. So the issue of weight of evidence, and I only have 3 minutes, what is the significance of a high similarity score? Well, as we said earlier, a similarity score has probative value if a high similarity score is only observed among matches or among bullets fired from the same gun. So one thing we can do is we can have a gigantic training set compute look at all possible pairs of bullets and essentially develop those two distributions of scores. And then if I have a case and I measure the similarity for that particular pair that arises in a case, I can look at the height of the densities, if you will. Let's suppose that I got a score of 0.75. I can look at the height of the density, the orange density at 0.75, divide that by the height of the gray density at 0.75, and that kind of gives me a likelihood ratio. So it's like a score-based likelihood ratio that tells me what are the odds of observing a score of 0.75 under the two competing hypotheses. So there's a few drawbacks, of course. The performance of the algorithm depends enormously on the data you use to train the algorithm, so you have to be very careful. This is the hardest problem, though. How do we define different source? We don't know that. Do we define that as guns of different brands? Is it the same brand but different models? Is it different brands but same caliber? We don't really know how these striations are produced. So we don't really know what it means to be different source. We're still working on that. And there's the issue of intractability, that all of these algorithms are a little bit of a black box, and it's kind of difficult to understand how the algorithm uses the different features to compute the score. Tragically, the case of Robert Stinson is not unique. This is what I was telling you about. I know a match when I see one. There's been very many cases. This is just one page from the webpage of the Innocence Project. There's been hundreds of people that have been recently exonerated after spending decades in jail for crimes they hadn't committed. So can we help create a fair system, improve the administration of justice? So we can. So we need to promote the use of statistics and data science to reach many objectives, right? First, we need to introduce some objectivity into the evaluation of evidence. This business of I know a match when I see one should not stand. Shatter the notion that you can make a categorical decision with absolute certainty. That cannot be done. And of course, highlight the fact that similarity doesn't imply same source. This is my team. This is the team that works on ballistics. I have a much larger team, but I just wanted to introduce them to you. And I'm calling all data scientists here. This is a very important area. tremendous potential for use in forensics, many important open problems. I really cannot think of an area in which we could have a stronger and more immediate social impact. Thank you so much.